Thanks. So let's solve today's code challenge. Check if number is a sum of powers of three. Given an integer n, return true if it is possible to represent n as the sum of distinct powers of 3, otherwise return false. An integer y is a power of 3 if there exists an integer x such that y first equals to x, 3 to the power x. So this is our first example. N is 12 and 12 can be represented as 3 raised to power 1 plus 3 raised to power 2. So we would return out of these examples. Now I would derive the logic. So let's see the constraints. Okay, 10 power 7. So at least n log n solution would be required. Now let's see how we can derive the logic through examples. So this is in the question it's given there should be distinct powers of 3. So this case is not done. Like you cannot return this case of 3 raised to power 0 6 times if the n is given as 6. The power should be distinct. Like this case, 12 equals to 3 raised to power 1 plus 3 raised to power 2. So here we can return 2 since 1 and 2 are different. Suppose n is 12. We would check for every power of 3 and see if it is less than n or greater than equal to n. If it is less than n, we would move ahead. 3 power 0, it's less than 3 power 1, we would move ahead. But here, 3 raised to 3, which is 27, it becomes greater than 12. So we would stop here and this would be our max limit. This is the max power we can take. And the powers above below it. So this would be our first step. We would subtract the highest power of 3 from 12. And this is the remainder we get. Now from 3 we would subtract the highest power which does not return us a negative value. If we subtract 3 raised to power 2 from 3, we would get a negative value. So we would decrement power by 1 and this 3 minus 3 raised to power 1 is giving us 0. So this is how we derive our answer for this. Now let us take some more examples. Suppose n is equals to 6. Again, I would do the same, deriving powers, incrementing by 1 until my power is 3 raised to power, that number is greater than equal to n. Sorry. So here 3 raised to power 2 is 9, which is greater than 6. So we would stop here. This is the max power we can take for generating 6. 1. So we would subtract this 3 raised to power 1 from 6. We get 3. Again, we are doing the same. And since both these 3 raised to power 1s are same, we will return false as these two are distinct. Again, I would choose a third example. Do the same power calculations until I find 3 raised to power greater than equal to n, greater than n, strictly greater than n. So this is that value. I would stop here and choose the previous value as my max power possible. Subtract it from n and see what I'm getting, 12. The max power I can choose is 2. Again, if I choose this power of 2 times, I would not be able to get the result as I need distinct powers, so I would immediately return false. Now I'm just converting this simulation into formulation and code. See, I was taking power value from 0 and incrementing it until it is greater than the number. So while power of 3 comma p is less than equal to n, I will increment path p. And if it becomes greater than n, I would just return the previous power value, break this loop, and get the power value. Now, until my n is greater than 0, if my n is greater than equal to 3 power p, I would subtract it from that 3 power p. And if n is greater than equal to 3 power p, I would just return false. Because first time I have already decremented it with the 3 power p. If again I'm choosing that same power, I cannot return to in any case. Lastly, I would decrement p by 1, and if this loop ends, my n would be equal to 0. So I would return true. Time complexity here would be O of log base 3n, as I'm dividing n by power of 3 every time. So the time complexity is log n, and our constraint is 10 power 7. So it will easily pass the constraint. We would not get TL. And space complexity is O of 1. We are just using variable. Nothing else. Second method. Let's see the second. Binary representation. So I'm representing 15 as a binary number, which is 0, 1, 1, 1, 1. And this would be the placeholder values 0, 1, 2, 3, 4. This is the k position. To convert this binary into decimal, again, what we are doing is multiplying this position with the power of 2 at this position. See, if it's this position into power of 2, which is 0th position, I'm multiplying it by same for the rest of the digits in the binary representation. Here we can see this 2 raised to power 0 is needed one time. This 2 raised to power 1 is needed one time. Also one time, this also one time, but this 0 times. So we can deduce how we can generate a decimal number n from a binary representation. Kth digit into 2 raised to power that digit plus k minus 1 digit into 2 raised to k minus 1 plus so on 0 digit into 2 raised to power 0. So same like we're doing it in binary representation, we can also um, showcase a number in its ternary representation. Instead of dividing by 2, we're going to divide by 3 and store the remainders from most to least, like we do in binary representation. So this would be the ternary representation of 12. The basic formula, instead of 2, we would have 3 here. And while representing it, this 3 raised to power 2 is taken one time. This 3 raised to power 1 is taken one time. How did we get this? We just divided 12 by 3. 3 fours are 12, remainder 0. 3 ones are 3, remainder 1. 3 zeros are 1, remainder 1, 0. So this would be our ternary representation. All of the powers of 3 are only taken 0 or 1 times first. So we would return true in this case. Now let's take 21. Well, again, I would do 3 sevens are 21, remainder 0, 3 twos are 6, remainder 1, 3 0, remainder 2. We got a remainder 2 here of any power, doesn't matter. We're getting a remainder of 2. That means this 3 power 2 is taken 2 times, which we don't know. So we would immediately return false. In ternary representation, if anything other than 0, 1 remainder, we return directly false. That's what we're doing. Here we are dividing 21 by 3, remainder is 0. 7 by 3, remainder is 1. 2 by 3, remainder is 2. So we would immediately return false from here. 15 mod 3, 0. 5 mod 3, 2. Again false. 12 mod 3, 0. 4 mod 3, 1. 1 mod 3, 1. 0 mod 3, 0. We got 0. So we will return proof 1. And no, didn't encounter 2. So basically what we are doing in this simulation is what we will write up as our code. While our n is greater than 0, we are at 0. If n mod 3 is equal to 2, we would directly return false from here. Otherwise, we would divide n by 3 and continue this process until n is greater than 0. If n uh, becomes 0, we would break out of this loop and return true, like in this case. Time complexity here would also be log base 3n, since we are dividing by 3 every time. So this will also pass our test cases. This is just a different method of solving the same question, because we're not seeing any difference in time complexity. Third approach. If the math solution is not coming in our brain, and a brute force approach, like just seeing the problem, we can reduce this. So this approach can also work in small test cases, not the large test cases. So n is 15, p is 0. We are starting from power 0 and n is our number, which is 15. We are picking this 0th power in our result or not picking. If we pick it, we would subtract that power from n. Our n becomes 14, power becomes 4. N is 15, power is 1, because we are not picking. Again, same from for this, picking, not picking. We pick 3 power 1, we get 15 minus 3, 12. N is 12, P is 2. Again, so on. This process continues. If we get n equals to 0 from any of the branches below, it doesn't matter if we get false from the other branch. We just have to find one such uh, combination where we find the result as distinct powers of 3. So we would do an OR here and return true above if we get true from any of these branches. Let's see a case where the tree is smaller so we can dry run it properly. Here we are picking p this power 0, so our n becomes 11, p is 1. Here we are not picking, so it's 12 when p becomes 1. Here, as p is 1, we are picking and subtracting 12 from 3, which comes out to be 9. And power here is 2, as we are on the next iteration. Here we are not picking, and so the number remains 12. Power becomes 2. And here we are picking, so 9 minus 6. 9 minus 9 is we got a 0. And power became 3. Here also we are not picking, and power becomes 3. But 3 raised to power 3 is greater than 9. So we would ultimately stop here, because even if we increment power, we won't get anything out of it. It would just go on. So we would truncate here so that our recursion doesn't go on for infinity and return false. We are returning true from here and false from here. So we do OR and return true from this above. From this function call also, we would return true above. And from this function call also, we would return true. And we would get our answer as true. Here also n is getting divided by 3. That many times we are getting these steps. So, and for each candidate, we have to walk through, either taking it or not taking it. So, time complexity will be 2 raised to the power of log n. And space complexity is again log n, because the recursion depth is the number of times n can be divided. So, this is our solution. Now let's code up all these three methods. Let's code up the first solution, equals to 0 by power of p. This would calculate the power of 3 with value 3. is less than or equal to 10, I would continue incrementing power by 1. Now, afterwards, while n is greater than 0, I will check if n is greater than equals to power of p comma p. Okay, p comma p. This I will just subtract the power of p comma p from n. Now, even after doing this once, our n is still greater than equal to power of p comma p. I would immediately return in decremental by 1. And if I break out from the while loop, that means my n has been 0 now, so I will return 0. Now let's check if it's passing all the speaker. Okay. Okay, here we have done a series instead of equal to subtraction. Okay, wait. N equals to n minus power. Okay, it's passing all the given test cases. All the hidden test cases are also passed. So it's done. Now let's forget the start everything with binary representation. Here, while n is greater than 0, n percentage of n mod 3 or n mod 3 is equals to 2, you will just return straight away false. If that's not the case, I would decrement by my n by 3 and then dividing it by 3 and return 2 if I break out 3. This is, let's check this. Passing to the test case. Yep. Yes. Time complexity though returns, sorry, remains same, right? Now let's check out the recursive approach. What's def solve? I would pass on n and p. If n is equals to 0 at any moment of time, I will straight away return from there and return 2 from there. Sorry, the power of raised to p ever become greater than n, I would straight away return false. Even if I increment power, it would not change anything. I would pick the power this time subtracted from n would be incremented by 1. In not pick case, I'm not picking the power. So n would remain same. Power would be incremented by 1 for the next iteration. I would return pick or not pick any time. I would return true if I get either of them. At last, I would return soil n comma Zero. My power is starting from zero. Okay, we have not defined. We have defined. Okay, it's passing all the given test cases. Let's see if it passes all the given test cases. Yep. Yes. But see how the recursive solution is not that uh, time efficient and space efficient. So this was it for today. Let's see you tomorrow. Bye bye.